Welcome. Today we're going to introduce Dynare. To begin with, let's discuss briefly what Dynare is. Dynare is effectively a front end to either MATLAB or Octave to solve and simulate dynamic stochastic general equilibrium models. Usually these arise out of macroeconomics, but they can be found in other places as well. To begin today, we need to review briefly a DSGE model so that we have a common basis to work from together as we introduce Dynare. So I'm not going to spend too much time on the economics of this, but let's look at it briefly. We'll use a household utility function that is additive and in logs as a function of labor and consumption. A Cobb-Douglas production function with an aggregate productivity shock process, Z. Our characterizing equations of this model are the intertemporal Euler equation and the labor-leisure Euler equation that arise out of the household utility maximization problem, as well as the household budget constraint. From the firm's problem, we have the equations for the interest rate and the wage rate, and we have a autoregressive first order process for our aggregate shock Z. We'll treat Z differently depending on our circumstance, but when we are dealing with stochastic models, we will deal with it in this form, where epsilon t is a normally distributed mean zero shock process. For convenience, we'll also use these other definitions for output and investment. Alright, let's dive into Dynare. Here we are in MATLAB. Now, in order to use Dynare, you need to install it on your computer. The process is very simple, and if you haven't done so already, go ahead and pause this and go to the Dynare website and follow their very good instructions on how to install Dynare on your computer. Once Dynare is installed, the first step is to create a new model file. You can do this in MATLAB by opening a new script, or you can do this with any text editor that you'd like. The only requirement is that when you save your script or text file, you save it as a mod file. Now that's done simply by adding the file name with a .mod at the end. So now we have our model file. This will be the programming front end for solving our DSGE model. A model file is very simple. This is one of the main advantages of using Dynare, is that you have very simple conventions for entering in your model and also specifying the types of computations you'd like MATLAB to perform. The basic structure of a model file is 5-part. The first part is called the preamble. Here we'll specify what our variables are, what our exogenous variables are, and what our parameters are, as well as initializing our parameters. The second part is the model block. In this section we'll specify the characterizing equations of our model, and you'll see that that is a very simple thing to do in Dynare. The third section of your model file will be to somehow specify how to find the steady state, or at least specify initial values for your model to begin at. You'll see when we get to this that there are many options for how to do this, and all rather intuitive. The fourth section is your shocks section. Here you'll specify either how the stochastic process moves, or in the case of a deterministic version of your model, you can specify deterministically what the shocks are. More on that later. The fifth and final section is the computation section of the model file. This is where you'll specify the things you want Dynare to compute for you. In this segment, we'll cover the preamble, the model block, and how to specify steady state and initial value section. In the next section of this tutorial, we'll cover shocks and computation. Okay, let's begin with the preamble. In the preamble, we begin by specifying what our variables are. We do this by beginning with the command var, short for variable, and then we simply type in what the variables of our model will be. In our case, we have output, which we'll call y. We have investment, which we have capital, labor, the interest rate, the wage rate, and consumption. We end every line in Dynare with a semicolon. The next thing we do is specify which of our variables are exogenous. We do this by beginning with the line with var exo, and here we'll specify the variable z as being our exogenous variable. We should make a note here about the different types of models. In this case, the way I've set it up, we'll be looking at the model as deterministic. In a deterministic model, all agents have perfect foresight about the shocks that will occur, and in this case, that epsilon shock process to our z is set to 0. It's known perfectly. So z becomes actually exogenous in this case. If, on the other hand, we were going to do a stochastic version of this model, z would be one of our endogenous variables, and we'd specify epsilon as the exogenous process, or rather our exogenous variable here. We'll do it both ways, but for now, let's start with a deterministic case, and we'll talk more about the distinction between the two models, and also the reasons you might want to use one versus the other in the way you set up your model. The next thing in our preamble is to specify our parameters. We do this by beginning the line with parameters, and we list our parameters. I like to use C's in front of my parameter names. So instead of just typing beta, I'll type C beta for constant, C delta, C alpha, CA, and then ending with a semicolon. The reason I started doing this was that beta is a function in MATLAB. So often the MATLAB code would get confused about this parameter that I was calling beta, and it would try to call this beta function that is a built-in function in MATLAB. So I started using the C's in front. You'll notice I also called investment INV for obvious reasons. I is a misleading, can be misleading in programming, as it also may look like an imaginary number. Finally, notice that I specified labor as LAB instead of just L. That's mostly because when I look at the lowercase l, I sometimes get confused with the number 1. So just for convenience, those are some conventions I use. You can use whatever you'd like. But be warned, with things like beta, you may not want to use names of your variables or your parameters that are also names of built-in functions in MATLAB. Now that we've specified what our parameters are, we'll initialize them. So we will say C beta equals 0.99. This is just like your normal MATLAB notation. Again, remembering that every line should be terminated with a semicolon. Delta we'll specify as 0.025. Alpha is 0.33 and A as just 1. That finishes our preamble. Before we move on, let's talk briefly about a couple things that you can do in Dynare as far as comments. Comments, single line comments in Dynare are done with 2 backslashes at the beginning of the line. So this line will be a comment. It won't have any effect on what happens in the computation. Similarly, if we want to comment out several lines in a row, we can do so with a backslash and a star. Everything following that will be a comment. We terminate multi-line comments with a star /. This can be useful in turning on and off the blocks of your model, as we'll see later when we switch between the stochastic and deterministic models. Alright, let's go on to our model block. Our model block is begun by entering the command model, again terminated with a semicolon. Everything after this model line and before our end command will be considered by Dynare to be characterizing equations of our model. One of the first things that Dynare will do will be to check that the number of equations we place between model and end is equal to the number of endogenous variables. So in this case, we should have 1, 2, 3, 4, 5, 6, 7 equations here. One of the main advantages of Dynare is this model block. There's a very intuitive notation, and you'll see that we don't need to especially manipulate our characterizing equations. We can enter them almost as if we were just writing them in a paper. This avoids tedious algebra and perhaps linearization and placing things in matrix form. Let's remind ourselves what the characterizing equations are for our model. We'll have 1, 2, 3, 4, 5, 6, and 7 equations here. Since we're using the deterministic setup at the beginning here, this equation for zt is actually not an equation that will characterize our model. So we begin by entering in the intertemporal Euler equation here. We can do so very simply. You'll see that the notation is quite intuitive. We specify the equations just as we saw them written before. 1 over c is exactly analogous to our 1 over ct in the document that we just looked at. When we get to this next part, you'll see that when we have a forward-looking variable, we can easily put that into Dynare by placing a +1 in parentheses immediately following the variable. Dynare will treat this as ct plus 1. Similarly, we'll have a 1 plus rt plus 1. Again, we do that with a +1 just following the r. And we end with the semicolon. I'm going to go ahead and finish putting in the next equation, which is our intertemporal Euler equation, not our intertemporal, rather, our labor-leisure Euler equation. You'll notice that the notation here is extremely intuitive. Next, we have our budget constraint and our equations for the interest rate and wage rate. Let's put those in next. Here we need to talk about predetermined variables. You'll see that I've written in capital the way that we wrote it in our characterizing equations, and probably a natural way to think about capital. But note that capital here is determined, the capital stock for next period is determined by the agents of the household's decision today. So in fact, kt plus 1 is determined in period t, and similarly kt is determined in period t minus 1. The standard way to handle these in Dynare is to specify each variable with the timing that corresponds to when it's determined. So in this case, we would actually put k minus 1 here and just k here. There's an alternative way to handle this, and that is to list our predetermined variables in our preamble. This is my preferred way because then I get to keep the notation from my paper consistent with the notation in my code. But you do need to remember to do this in your preamble. You can specify which variables are determined a period before your notation would suggest by saying predetermined underscore variables, plural variables, and saying k. Note that you need to place your variables both in the variable list and in the predetermined variable list. So now I can use the same notation. Note that we didn't have this problem with C or R because those are determined in the period that they show. Alright, now we have R equals. The notation for the exponential is the same as in MATLAB, exp parentheses around the thing you're exponentiating. Here, that's C. Finally, we need to put in our last two equations. The first was for y. Whoops. And the last is for I. And we'll save that. Let's check very quickly. We have 7 variables that are endogenous, and also we have 7 equations in our model block. So that should work. And that's it for the model block. Like we said, this is very intuitive. There's no linearization necessary. There's no matrix conformity that we need to do here. It's simply writing the equations as you would see them in the paper. And note that we have in these equations only one variable on the left-hand side, just a single, as you would see in MATLAB. But that's not necessary. For instance, here we can assign the equation as 1 over c, and probably more instructively, this equation clearly wouldn't be okay to write in a MATLAB syntax, but Dynare can handle our equations that way. So it's a very flexible form here. Now that we're done with the model block, we'll move on to specifying our initial values. Now, the initial value block has different purposes for stochastic and deterministic models. In the deterministic model, note that we don't need to compute technically a steady state as we would in a stochastic model. More on that in a little bit. But if you want to begin your model simulations in a steady state, we're going to need to specify or find the steady state and or specify it directly. Otherwise, we may want to begin our model simulations in a non-steady state situation, equilibrium. To do so, we need to specify the beginning values for the model simulations. This is where we will use the initial value block. In our setting, we'll for this tutorial, we'll want to begin our model in a steady state. We begin our initial value block by typing the command init val, again terminated with the semicolon. We're going to specify what will be close to a steady state but perhaps not exact, because we don't want to go through the tedious work of finding the exact steady state on our own. Luckily, MATLAB has, or Dynare employs several solution techniques to help us find the steady state. And finally, Z. Note here that I'm not specifying initial values for every variable, giving Dynare a starting place to find the steady state will be good enough. To instruct Dynare to find the steady state and also to begin simulations from the steady state, we simply use the command steady. Now, the steady command will work very well if our initial values are near a steady state. Unfortunately, finding a steady state is difficult, and the techniques that Dynare will employ are not likely to do very well if we don't start our searching near a steady state. So this becomes a little bit more of an art than a science, but we'll abstract from discussing detailed ways of finding the steady state at this point. Note, though, that Dynare will let you find the steady state either by using these MATLAB solvers. You can specify different solvers to use by using these solve algorithm option for steady. There are 4 different options, 0 through 3, that can be found. Details on the differences between all of those can be found in the Dynare documentation. For our purposes, we'll leave it at that. Another option in finding the steady state is to log linearize. Dynare will automatically find a steady state if we've linearized. The problem with log linearizing, and it should be noted that the reason Dynare can find the steady state so easily is that all of the variables are specified as percentage deviations from a steady state, so the steady state of the log linearized model is 0 everywhere. The problem with log linearization is that if your model includes any kind of sum, which is likely to be the case, you'll end up with ratios of steady state values in your log linearized model, so you'll still need to find the steady state values of those and specify them as parameters. So that's a downside of that. Also, log linearization can be very tedious, and one of the primary advantages of Dynare is that you can come up with better than linear approximations without doing as much algebra to set up your model. Another way to find the steady state is obviously to find it yourself using some sort of external program. You can write, if you have access to Maple or other packages like that, Mathematica perhaps, you can find it on your own and specify the exact steady state in the initial value block. In that case, you would just remove the steady command after the initial values, and Dynare will just begin from that steady state. Finally, you can write a MATLAB program that will aid Dynare in finding the steady state. To do this, you simply create a script in an M file, and you name it your model name, so in this case example, and then underscore steady state, all one word. And like I said, that's an M file. More documentation can be found on the Dynare website on how to do that exactly, but that is an option as well. So in our case, we should be able to use just these initial values and the command steady to find our steady state. In a stochastic setting, a steady state is required. Dynare will compute up to a third order approximation of our model, but that will have to be about a steady state, a Taylor series approximation of our model around the steady state. So in this case, our initial value block is required so that we can, and furthermore, we need to specify a steady state. Exactly. So either we can, once again, specify an exact steady state in our initial value block by solving it for it some other way, or we can put an approximation in and use our steady command just as before. If you want to start from a steady state in your simulations after in your stochastic setting, whether or not you've entered a steady state exactly in your initial value block, type the command steady after the block, and Dynare will begin your simulations of your stochastic model from the steady state. And that will apply also to your impulse response functions that you may want. Note that this is probably a good idea, because in our Taylor series approximation that we'll be doing about the steady state, it's important to be near the steady state, otherwise our approximations can be very poor. So starting somewhere other than the steady state in simulation can result in large approximation error and can be problematic and cause our results to be unreliable. Alright, at this point, let's take just a few moments to create another file that is the equivalent of this file, but with the stochastic shocks incorporated. So we'll move from a deterministic setting to a stochastic setting. We'll save this one and then create a new script, and this one will save as example stochastic.mod once again, and here we'll just take everything from this model, from our original model, and paste it here. Save that. Now though, we'll specify z as an endogenous variable and epsilon is our exogenous variable. In this case, we have one more exogenous or endogenous variable. Naturally, we'll need another endogenous equation. This will quite naturally be the law of motion for our endogenous, or for our z shock. Note that -1 works just as the +1 will. And also note that here we've only used plus and -1. If you have a model that is forward-looking 2 periods or backward-looking 2 periods, you can use +1, +2, +3 all the same way as we've been using +1 and -1. I do have another parameter, rho, and we can initialize that here. And we'll save our stochastic version of the same model. Alright, that's it for this segment. In the next segment, we'll discuss the shocks section of the model file and also computation.